3 thirds. So it is 3 point. Oh, notice the unit. Oh, something wrong? No. Yeah, something wrong. 20. Right? 20. 320. So it is 6.
667.
17. Yeah. So the third step, now we get the responses of the source acting individually. Now third step, we use the superposition principle. Is IT equal to IT1 plus IT2, and VT equal to VT1 plus VT2. So IT is 0.333, right? And VT is
11.667.
So understand?
Yeah.
Anyone have the problems of the superposition? If you have problem, just say it out. If you don't say, I will go with another part.
Okay.
Why is it more okay? Okay,
Okay. Now it's the last part of this chapter. The Western Bridge is.
So, Mom, do you want to say something?
What are you calling?
You have problem? You have problem with the superposition?
I think so. What?
Some problem of this.
How became 0.33? What point?
Which
IT.
IT.
Yeah.
We have solved IT acting by the sources individually, right?
And then it's 1 and 0.33. Oh, yeah. Okay.
And the Western Bridge, it is also a small point in this chapter, but I think maybe it may be useful for you because it usually applied in the mechanical engineering. This circuit is used to measure the unknown resistance. That is, this is the Western Bridge, and we don't know the Rx. If we want to measure the volume of Rx, we only use this bridge, and this you take it out. This is a device, and we take this points. We take this resistance in the 2 points, and when the detector is 0, that means there's no current flow to this branch, right? If the detector is 0, that is no current flowing from this branch.
Yeah.
You can regard it as, now this branch can be regarded as open, right? Because there is no current.
0.
In your real application, you must use the device to detect the resistance, and you can see the detector when the detector is 0, and because the R2 and R3 can be changed. You get the R2 and R3. Now, as it says, now IG is 0 and VAB is 0, right? You understand? When IG is 0, while VAB is 0.
Yeah.
Understand, right? So now the Rx can be calculated by this equation. This is the result. How to prove? there is a answer on your book 75, and maybe I will deduce it. Now, if this is a 0, right, and this branch these two branches are in series.
I1.
I1
Yeah, 1.
So I1 equal to I3, right?
Yes.
Now, when the detector is 0
Mm-hmm.
and IG is 0 and VAB is 0, right?
Of course.
So now I1 equal to I3 and also I2 equal to I4, right?
Yes.
Because VAB is 0, right?
Yes.
And the voltage across these two branches
Yes.
are equal to the voltage across these two
Of course.
branches because they are in parallel.
Yeah.
So that is, if VAB is 0, that means the voltage here is equal to the voltage here.
Of course.
Yeah. So that means I1 multiple R1 equal to I2 multiple R2, right?
Yes.
And also, the voltage across this branch is equal to this one.
Mm-hmm.
That means I3 multiple R3 equal to I4 and R4. So,
X, right?
so
RX.
Rx. So combine these two equations. You can use this one, divide this one, right? Use this one, divide this one. Or that is I3 R3 over I1 multiple R1 equal to I4 multiple Rx over I2 multiple R2. Understand?
Yeah, we stand.
Understand? Yeah. Now, I1 is equal to I3. So, right? And I2 equal to I4. Now it is R3 over R1 equal to Rx over R2. So, Rx is Rx is R2 multiple R3 over R1. Right? Is that the question? Now we prove that. Okay? So, in your application, you just need to remember like this. Rx multiple R1 is equal to R3 multiple R2. That means the branch, the opposite branch, the branch of the bridge, the opposite side multiple together is equal to the other side, the other two sides multiple together. Just remember like this. This branch multiple the branch opposite are equal to another branch of multiple, yeah, the opposite. So don't issue, I think it's a little difficult to remember this, but you just remember. You just remember like this. Rx multiple R1 equal to R2, R3. No matter if this is R1 and this is R2, no matter how they marked,
Yeah.
you just remember we use these two bundle together and this equal to these two. Right? It's easier to remember, right? So, no, this won't work. So, do you have, that's the whole contents of this chapter. Do you have some preference of this chapter?
Somewhat.
Some preference. Now let's review what we learned today. We have learned many small points today. Many small points. Maybe in our last previous class, we just learned 1 point, the source transformer or some others, and we do a lot of training. And today we learned at least three or four. The first is maximum power, PMMX, and how to get the maximum power of the two-terminal circuit. The first step, we transfer the circuits to the Thevenin's equivalence, right? When RT equal to RL, it gets the maximum power, right? That is RL equal to RT. And this is the first point we learned today. And the second is maybe we can remember it together. The efficient.
PL over PX.
Right? Yeah. And third is the superposition principles.
Yes. So good one.
Yeah. The superposition principles, we have do an exercise, so I think maybe all of you understand it. Just the theory, just this page. Yeah, superposition. I will write now. And start is the Wheaton bridge. Calculate the. You don't need to remember R1, 2, 3 or other. Just remember the opposite side, multiple together, and we can get the Rx. So this is one we learned today. Do you have some problems? No problem.
Yeah.
Now we will receive the, I think maybe we will review the chapter 2. Because I find that when I introduce the Thevenin's equivalent, you forget the voltage and current division. So I hope all of you can review the contents of the class. And this chapter, the first task for us is to solve circuits by combining relays in series and in parallel. I think maybe you do it very well by combining the resistance in series and in parallel. And second, apply voltage division and current division principles. I don't know now. can you solve it? For the voltage dimension, maybe for voltage dimension it is relatively easy.
Yeah.
If the two resistors in series and V1 is equal to Vs multiple R1
R2.
R1.
R2.
R1.
R2. Rashi, please continue.
R1.
R2. This is the problem.
who says it is R1?
It's not two.
R1 can you-
Because the
can you
voltage
have-
is one.
I'll show it. I'll show it.
When it is
But
one.
R2, I
R2.
think it's R2.
R2, Rashi.
R1.
Voltage across R1, right?
Voltage.
Across R1.
Rashi, R2.
It's R1.
It's R1. The voltage is across R1.
Why?
This is voltage division.
Formula.
That's current division.
No need to say why.
One or two?
R1.
Yeah.
Chao
Wait.
What does she want?
What's your problem?
It's a formula.
No, Lava, go back to
That is series, right? And I in the center range.
Mm-hmm.
And V1 equal to I multiple R1, right?
Yes.
And this part is a current, right? Because I is equal to
Yeah.
Vs over R1
Oh.
plus R2. And for the current dimension, I1 equal to I maybe I
Yes.
IS or low. S is a short circuit, maybe IN. Just I. R1 plus R2 it is R2.
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 You can understand like this. For the resistance parallel, the voltage of each branches are equal, right? So the I. Oh no, you cannot.
Yes.
Yeah, you can. It is not equivalent to the voltage source. For the current, I think for the current for the current dimension, this is the steps to get the results. But I think it's better for you to remember these two together because they are this is R1 and this is R2. You can remember it. If you want to remember, I think the first step you must understand how to calculate the voltage dimension, and you will get R1, right? If you understand this, and you can remember this as R2 now.
Yes.
But for the current dimension, it is just for the two resistors in parallel. If I have three, you can always use this directly. I think you may review the.
Rashi, can you review the Thevenin? Nothing.
And the third, yes, I will. And the third one and fourth one it is not.
No need, okay? The third one?
Huh?
The third one. No need, right?
Yeah.
Yeah, it's a good
So it
for
is.
me.
Yeah, it is not. It is not necessary for the students in mechanical.
Yes, it's a good news for me also. I can
But-
understand this one.
But it is the main solution for it is to use the KCL and KVL.
What?
the low voltage or the merge current method is to use the application of KCL and KVL. But it is only use the equations to combine a equation set and to solve the equation set. So you can also understand it as the KCL and KVL. It is no other new knowledges.
Not only KCL and KVL. It's like V1 minus V2, V3 minus V1. It's confused.
But that one is not that means to the 3 and 4, and I think it's a problem of
Yeah, that's why I said.
yeah of the first one or first two. You mean the direction, right?
No, not voltage.
No voltage.
Yes.
What's your problem in no
The
voltage?
problem is to find the voltage. Which one have to calculate, like V1 minus V2 or V3 minus V2 in node.
You just use KVL.
How to use this is the question.
You just use the KVL and notice the direction of the
Yes,
voltage.
direction.
Yeah.
Direction is.
Can you draw a finger? What you don't understand? Come here. No, don't give me an example because I have no much time.
Like this one. 58.
Okay, maybe we can discuss after class and I will go over it because there's no much time left.
Yeah.
And the Stainless and Norton's equivalence, you have some problem with it. The Stainless for, I think all of you can understand what is the Stainless for.
No, actually, I think the problem is the nodal analysis.
Huh? No?
Yes, exactly.
The nodal analysis is easy, but sometimes when you
You
have
mean
to.
this one?
Which one? Node voltage. Yeah, actually, let's try the node voltage technique.
I did introduce this theory in the class because this content is can be learned by yourself. It's not for your mechanical students. If you have some problem with this part, I will discuss with him after class. Okay. And the next one is maybe the sixth and the seventh I don't mention because that is what we learned in class. And the fifth one, the seventh and Norton's equivalence, we have introduced 3 methods to solve the circuit, right? The first is I take the seventh equivalence as an example. The first is calculate the open circuit voltage, right?
Yes.
And the short circuit current.
Yes.
So RT means the Stainless equivalent resistance equal to VOC over IAC. And the second method is to get the VOC if it is the Stainless equivalent. Get the VOC first. If it is Norton, you get the IAC first. And how to get the resistance? You can zero in the source and get the RT directly by the resistance in series and in parallel, right?
Equivalent.
And the third maybe is the most convenient one. Third by the third method.
Which one?
To get the third method to get the Stainless equivalent. Okay? Source transformation. Source transform. Right? We can use the source transform to solve every circuit. I transfer this to the Norton's equivalent and we can combine the source and resistance together and then transfer the Norton's to the Stainless and combine the whole circuit to this one or the Norton's form. So this is chapter 2, and this week we'll start with chapter 3. So class is over. Thank you.
Chapter 3, bro.
Okay, you can have a breakfast now. And you have some problems, come here.
Maybe viewers.
Don't want to go?
Huh?
Can I see your notes for yesterday? Physics.
I'm down.
Yes, save it.
Chico.
You know shit. Bro.
No, I
I found all people.
You and
I was in the last.
you learn to no, when you learn resource, you can solve it directly. Don't use your payment. You use the not payment.
Yeah, VPN. Is your VPN on?
Yeah, Mohammed, you say bro, lava today.
It's on?
I mean, it's lava.
It's working.
Of course, bro. Let me show you.
You show me what?
Let me show you.
Oh, on me.
How long?